Good morning and good afternoon, everybody. I'd like to just give a quick introduction about our presenter. Today, you will be hearing from Robert Ferrulo. He's a senior technical marketing engineer with Mojo Networks, with over 20 years in the networking industry and nearly a decade in Wi-Fi. He was formerly at Maru and Alcatel. And I'm going to go ahead and kick it off to you, Robert, so we can begin today.
All right. Well, thank you very much, Erica, for that introduction, and welcome all. We got a lot to cover today, and we're going to go pretty fast. And before we get started, I should say that we have been working on a campus deployment guide, which is going to be published pretty soon. And so we'll have that available via our website in the near future. So please do look for that. And that goes into great detail into what we're going to be touching on here today. And it covers much, much more than just doing capacity planning. So please do look for that. Or you could reach out to your rep, and they can make that available for you. Okay, now let's get started. So for the agenda today, we're going to be going over a simplified wireless LAN capacity planning session. And we're going to be doing that for classroom situations with multi-user MIMO and without using multi-user MIMO. We're also going to talk about multi-user MIMO again, just to review the capabilities or what's happening, the mechanisms, and then we're going to talk about the benefits. We're also going to introduce the C120, which actually we announced was earlier in the month at NRF, and so that's a Wave 2 platform. That's our first Wave 2 platform. We'll talk about that just briefly. And then we'll have time for some Q&A towards the end and talk about how you can get the free access point. All right, let's get started here. Okay, simplified wireless LAN capacity planning. So, I should also mention that we did a full series on 11AC, and that, from the introduction to deep dive on all the features to a full session on channel capacity planning and deployment best practices and network optimization and so on. And those webinars, the videos of those webinars they're available also on our website. So if you're interested, you can download those for more details about 11AC. All right, so this is one that I love to talk about because it's, we have a planner, and, we have the Mojo Planner, which can help with the predictive site planning and all that. But, most of those planners, the way people will run those, and ours no exception, they'll do it by a floor of a building or something like that. And then it assumes that, it's making the assumption that everything's going to be constant, throughout the whole, the floor. So all rooms are going to have the same type of requirements. And here we get down into we want to get down to the room itself, whether it's an auditorium, a lecture hall, a classroom. We want to really focus on the requirements for that space. And so that's what we're doing here. We're calling those requirements for that particular space a use case. So in the use case, we got to find out about, of course, the client, the applications, and the usage patterns. And we're going to need those to do our little calculation. And also we need to know about the building, the size of the space for the use case, if there's any obstruction in the area, which will affect attenuation and so on. Also, we have to find out if we have neighbor APs or any other type of interference, whether it's Wi-Fi or non-Wi-Fi interference. We have to also consider what kind of spectrum we have available. Are we in a region or in an area where we can't use DFS channels? So we're going to be limited to a smaller set of channels to work with, which would make us have to use we'd have to go to a 40 megahertz plan instead of an 80 megahertz plan, for instance. All right, here's this one. I was surprised. Did some research and trying to find out what type of clients are available. We can't go to Wave 2 solution if we only have Wave 2 APs. Obviously, we need Wave 2 clients because they're, if you could use Wave 1 clients with Wave 2 APs, but you wouldn't get nearly the the benefits if you were to do that. So on the right-hand side, you see a bunch of Wave 2 clients. Now, this is just a subset. There are actually way more. I just picked some of them that I thought would be interesting, but there really are a lot more Wave 2 clients available or soon to be available. And as we buy new phones and new tablets and new laptops over the next 2 years, next year, 2 years, we're going to be we're going to buy Wave 2 clients, at least here in the U.S. and a lot of other regions as well. So we will have a lot of Wave 2 clients available, or actually in our pockets, or we're carrying them in our backpacks in the very near future, which is really good because as we talk about multimedia MIMO, we'll see how important Wave 2 clients are. All right, bit rates. I just put this up for reference. These are estimates or approximations. They're not, for sure. Your mileage may vary, so to speak. I started with the lowest bit rate all the way up to the highest bit rate. And you can see down at the bottom, we have one. It's pretty high, and it's coming. I don't think too many schools are using 4K today, but we've all seen how much more engaging high definition video is. And, video is a huge part of curriculum. I'm sure many of you know that if you're in the education space, video is a very, very big part of curriculum in K-12 certainly, and in higher ed, because it's a very good way to communicate some things. And so it's being used because it's effective. And the higher quality of the video, you can say, the more amazed, that people get when they can see something, or the more engaging it is, the more compelling it is. So we can see that right now, a lot of folks are using 720p, but some are even starting to use 1080p. And as we get the capabilities for the network and the devices, we'll probably start seeing 4K for certain things, like for larger displays where it matters. So we'll probably start seeing that in classrooms. And again, very important for our calculations. This is a pretty good graphic of the spectrum available here in the U.S. And other regions, of course, it's going to vary. But here in the U.S., I put this up there because I wanted to point out a couple of things, really. First of all, pink, that's spectrum that's been identified by the FCC. And it's not available yet, but and I don't know the dates when it will be available, but it looks like it's going to happen. So if we look here and we look at the 80 megahertz channels, we have we're going to end up with another 3 80 megahertz channels because we already have this 165 here. So if you go out to Uni 4, that'll make up another. So we'll get 3 additional. But without that pink, soon to be available, hopefully, if we just look at all the others, and we have the gray and the yellow. The gray and the yellow represent DFS channels, but people have shied away from DFS over the years, and for good reasons. One of the main reasons why, because you had a lot of clients that didn't support DFS. That's not true anymore. I mean, now most clients that are out there, unless you get some really old clients, you're going to have support for DFS. And we're going to be deploying every network pervasively in 2.4 as well as 5 gigs. So if there are some clients that don't support a DFS channel, they'll be able to jump on the 2.4 in that area. So let's count them. 1, 2, 3, 4, 5, 6 DFS channels, 6 80 megahertz DFS with DFS, or rather 2 non-DFS and 4 that are DFS. And so I'm recommending going with 80 megahertz because that's how you get your most bang for your buck when you go from 11N to 11AC, is by doubling the channel width. And a lot of folks have already done that. They've gone with 80 megahertz. So if you need the extra capacity, we recommend that. The solution we're going to talk about today for the classroom is with 80 megahertz. All right, so let's move on here. All right, so this is for max data rates. I'm trying to set the context here, or just we're going to be working back from this, which these are max data rates. And of course, they're not throughput rates. We all know that, just max data rates. So for instance, if you have a MacBook Pro at 3 spatial stream and you connect to an 80 megahertz 11AC access point, wave 1 or wave 2, the max data rate that you can connect at would be 1.33 gigabits per second. But that just tells us what the max data rate is. It doesn't tell us the throughput rate. Throughput rate, and if you have again taking that same MacBook Pro and connecting to a wave 1 or wave 2 11AC access point, it's 80 megahertz, and you're 10 feet away, 20 feet away from that access point, and it's a perfectly clean channel, and you're using Chariot or iPerf or some other tool to do some performance testing. Getting 798 would be a good run. It wouldn't be the best run. You can get over that, but that would be a reasonably good result for a single client connected to an access point, very close to an access point, and using the whole capacity of that access point, or at least that radio, the 5 gig radio. Now, that's not a real use case for the most part, because most use cases are going to have more than one client, and they're not always, the AP and the client aren't going to be very, always close to each other. So we have to start thinking about what happens when we add more clients and when those clients are at different distances from the access point. So let's go to this other chart here, and we see that now we have for low density throughput, we have anywhere from, we say from 1 to 15. Actually, I should change that from 2 to 15. But if you have just 2 clients, of course, these numbers would be higher. But you have to, you have to draw the line somewhere. So we're going to have low, we're going to have moderate, we're going to have high, and we're going to have very high density. And these tables, we just put them here for reference, because when you're trying to do calculations for channel capacity, you have to factor in loss due to contention. If you don't, then your numbers are not going to be close at all. You'll actually end up usually underestimating how many access points you're going to need to accomplish something. So we say that this would be for taking that same MacBook Pro, or not one MacBook Pro, but in this, say we have 10 MacBook Pros, or 12 or 8, they're going to be sharing approximately 465 megabits per second. So they're going to share that. They're not each going to get that. It's a hub-like behavior when you're talking about Wave 1 or 11N or legacy Wi-Fi. It's always a hub. It's always going to be a single client and single conversation between that AP and one of its clients, right? There's no talking to multiple clients at one time until you get to Wave 2. So we have 465 megabits to share for those MacBook Pros. Okay, and we say here we have a minimal loss, about 5% loss due to contention. We also have loss of, we're saying around 20%, and that's loss because some of the clients are going to be legacy and 11N and then 11AC, Wave 1 and Wave 2. Basically, what we've done is we looked at, if you just take 5 clients and you put them right near the access point, 10 feet away from the access point, and you do a test, you look at the aggregate throughput, then you go with 10 clients, then 20 clients, all the same clients, by the way, and then 30, 40, 50, 60, and you can then see the pattern of contention loss. And you do this for different vendors' access points. You don't just do it for one. And then you can come up with some estimates of the type of contention loss you'd get as you grow the number of clients on a single radio. And for the loss due to signal strength and degradation, which is estimated to be 20%, there you're placing 10 clients or 20 or 30 clients at different distances from the access point, and you can see the impact that distance has on the loss. So that's how these numbers were derived. And again, it's not for one particular vendor. It's really just a snapshot or a survey, if you will, for different capabilities and enterprise class access points. All right, now here we got moderate density, and we got this. I'm going to focus on the single spatial stream because we're going to use that in our example for the classroom. And we have from 16 to 30 clients. And let's take a look at the single spatial stream. I'll go back here. And so single spatial stream with just a single client would be 260. And then we'll go to low density. Now we have 151. And then down moderate density, 139. And again, that's going to be shared amongst the clients. And we say we've got about 8% due to a loss due to contention. And then finally, 117. And so that 139 number, we're going to use that in our use case examples for the classroom. So keep that one in mind. And that would be for moderate density up to 30 clients. All right. So you can see as we go to high density, we have 27% of the max data rate. So now we're down to 117 to work with. And then very high density, you can see we're sharing 87%. So there's a big loss due to contention. And that's one of Wi-Fi's Achilles heels, really, is the loss due to contention. It just, as you start scaling, it really, your efficiency goes down. And that's, it's just the way Wi-Fi works up until multi-use and MIMO, and we'll get to that next, because multi-use and MIMO is going to, basically help us with efficiency. Big deal. Now here's a simple formula to do calculating a calculation of the channel capacity requirements. It's just two steps. First, we need to find out the per device airtime. So we take the application bit rate. That would be what you'd like to do is you want to design for the worst case scenario. So if the worst case scenario for a given use case is HD video, then we'll design for that. So let's say the HD video is 4 megabits. Well, that 4 megabits, we'll use that for the SLA, or basic service level assurance. So we want to make sure that each client is able to get that SLA for that particular use case. And then we divide it by the channel capacity. And remember, the channel capacity is going to vary based on how many clients you have on a particular radio. So if it's low density, high density, what we just went through in those charts. So we use those charts to determine the channel capacity for the particular use case. And then we just get the percentage there, multiply by 100, get a percentage of airtime. So that's one device. How much time will it need? And in step two, you just take the total number of active devices and you multiply that times the per device airtime, and then you'll get the total airtime required, and that will be in a percentage, and then you just basically convert that to channels, unique channels. Of course, we can't reuse the channels in the same area. That would not help us. We're going to have unique channels, non-overlapping unique channels, and then you'll get the number of radios required, channels and / radios required. So it's very simple. And it really works from experience, so very useful. Okay, I'm going to review multi-user MIMO really quickly here, but first we'll start with SU-MIMO, single-user MIMO. So we have a 4 spatial stream Wave 2 AP there, and we have a single spatial stream client, and we have 80 megahertz channel, and that client is capable of doing 433, a data rate of 433 megabits, but an expected max throughput rate. If everything's clean, the channel's clean, the client's relatively close to the access point, choosing the highest data rate, you say about 260 megabits. That would be a good result. And so you're only using you're getting only one spatial stream worth of throughput out of the 4 spatial stream AP. So effectively, you're using 1/4 of the AP's throughput potential there. And in a lot of classrooms, or a lot of use cases, not just classrooms, it could be auditoriums, lecture halls, it could be sports venues. A lot of people will have single spatial stream devices or 2 spatial stream devices. Phones these days, the phone I'm using is a 2 spatial stream phone, 11 AC, so a lot of handhelds are going to be 2 spatial stream or 1 spatial stream. All right, and here we go now, beamforming. Or actually, multi-user MIMO. So it does use beamforming, of course, and so it's downstream only. You can support up to 4 clients simultaneously, and the AP is going to use the channel state for the individual beamformees to calculate a composite steering matrix. So when it talks to all of these clients, in this case there are just 2, it can be up to 4. It's going to send it, obviously the signal is going to be transmitted to all of them simultaneously, but we're going to be creating these peaks and valleys, so to speak, or these beams and null beams, as you can see here, so that the information that's destined for this client is strong here, whereas the information destined for the client at the bottom is weak here, or a null beam there. Now, the null beams do raise the noise floor, and so your mileage is going to vary. You're probably not going to be able to support the highest data rates here because of the noise floor being raised by the null beams. But the idea is to have this constructive interference here for this guy and destructive interference for this information here with respect to that client, but constructive there. So again, it goes into beamforming, constructive interference or destructive interference. And you can, of course, go to those webinars that I was talking about that are available where we go into this in more detail. We go into beamforming in more detail as well. All right, so that's high level anyways of how multi-user MIMO works. So if we then step forward and we have the same, say the 120, which is a 4 spatial stream Wave 2 AP, and we have 3 clients, a 2 spatial stream and 2 1 spatial stream clients. Now, the aggregate max data rate of these clients altogether would be 1.733. That's if all three of them were operating at the peak data rates. The aggregate then would be 1.733 because that's what the aggregate is for 4 spatial streams. But the aggregate throughput would not be 60% of that, not likely. So we don't get 100% efficiency when we combine these 3 devices. So if this were a 4 spatial stream client as opposed to 3 clients that total 4 spatial streams, if we were to get 0.6 of this or 60% of this, we come up around 1 gigabit per second of throughput. But with multis and MIMO, we're not expecting it to be that efficient. It's going to be better than talking to one of these at a time serially with MU-MIMO, but we don't expect it to be 100% as efficient as as if we were talking to a single client that's 4 spatial streams. But it's still better than talking to each of these serially. And how much better? Well, it's going to depend on a number of factors, like how spatially differentiated these are, and the RF conditions, and the channel state, channel conditions, and so on and so forth. But we still do see we're going to get a gain here. So we know we're going to get a gain in efficiency. More testing. We're going to have to do much more testing, and over time, we'll all learn just how effective multis and MIMO is at improving performance. All right. So yeah, it works better if you have a mix of 1x1. Actually, 1x1 would even be better than 2x2. So if we have 4 1x1 clients, we expect to see an efficiency gain over, say, 2x2 clients. Okay. Moving on. All right. So yeah, the amount of boost in performance depends on a number of factors: channel conditions, spatial differentiation of clients. We say spatial differentiation. We don't mean necessarily how many feet they are distant from each other. They can be, just a few feet from each other, but spatially, in terms of how multis and MIMO, how the wave in the channel state, the waves are going to propagate, and with the reflections and all. So they could be spatially differentiated, even though they're only, like I said, a few feet from each other. If anyone's done any testing, you can just rotate a client and get a completely different performance. So it's the same place, but you just rotate it, like say 90 degrees, and all of a sudden you see a 30% increase in performance. It's because you basically change the spatial relationship with regards to multis and MIMO, and between that client and the access point. So anyways, just something to think about there. Client density, and we see we're going to have a fair high client density in certain places like auditoriums and lecture halls and gymnasiums and sports venues and so on. In the education vertical, libraries perhaps, cafeterias, but also classrooms. Classrooms are going to be up to even 40 devices active simultaneously, and that's a big classroom, but you can have that many. Wave 1 to wave 2 mix. Yeah, this is going to make a difference. If you have mostly wave 1 clients, then you're not going to get really the big benefits from multis and MIMO, because it requires wave 2 clients. The ratio of 1x1 to 2x2 versus 3x3. Yeah, you're going to use this for 1x1 and 2x2 clients, and the more 1x1, the better. But if you have just a lot of 3x3 clients and very few 1x1 or 2x2s, you're not going to see the gains. So, all right. So based on early testing, the gain is somewhere around, we can say safely around 50%, up to 50%. All right. So just a little bit about the 120. It's a wave 2, and it's a true wave 2 because I highlighted some of the features here, and it's 4x4 MU-MIMO. Earlier generations of wave 2, they didn't support up to 4x4 multis and MIMO. They would basically only support 3 devices. So that extra one gives you 25%, greater efficiency of multis and MIMO. So that's important. And then also, here's the big one. Now, I did show you the chart, and with the spectrum that's going to be made available, additional spectrum that's made available. But if you look at the 80 plus 80 or 160, now, most use cases in education will not use 80 by 80 or 160 today. But in the future, we can conceive of some, imagine some use cases. For instance, let's say you have an auditorium, and maybe this is more applicable for higher ed, but it could be for K through 12 as well. And you put 2 access points in there today, and they're 80 megahertz. Now, fast forward to a year from now, when the FCC's opened up more spectrum, and all of a sudden you realize that you need greater capacity in that auditorium. If you can use DFS channels, and now all of a sudden you have 120 more megahertz of channel to work with, you could take those APs and instead of having 80 megahertz, turn on double the size of the channel width, and you just effectively double the capacity in that auditorium for throughput. So that would be something to think about. So the 160 or the 80 plus 80 is kind of like future proofing your investment. All right. Now here we go. Last part. We're going to talk about the classroom use cases. So for both use cases, we're going to keep things constant except for one thing. This first use case will have Wave 1 clients. All right, we'll have 25 of them. They're going to be active concurrently in a classroom, a single classroom. We're going to have adjacent classrooms, but we'll just focus on one classroom. And the adjacent classrooms will also have 25 devices active concurrently, and they'll have a 4 meg SLA. And the DF channels are available, so we can easily use 80 megahertz. We'll have 6 non-overlapping 80 megahertz channels to work with, no problem. And the walls are low attenuation, so we'll definitely need to basically use non-overlapping channels for several classrooms within an area, which we'll have plenty of. We'll have 6 channels to work with. All right, and so just using that simple process that we talked about before, step 1, where we're going to take the Wave 1 clients, so we got 25 of them. So we're going to have moderate density. So remember that 139 on the tables that I went through for moderate density. We have that number here. And we have HD video, 720p, and it's averaging at about 4 megabits per second. We do the little calculation where we learn the percentage of per device airtime, and that's 2.88%. Again, we're using 80 megahertz channels. And so 2.88% per device, and then we just multiply that. Step 2, we just take the number of active devices times the per device airtime. We get 72%. So we round that up. We round it up to a single AP. Of course, we'll have additional capacity there to grow. But anyways, we round that up, and we have 1 AP per classroom solution. So now a lot of classrooms, for you folks out there that have done designs for networks, a lot of schools don't have 1 AP per classroom. Some do, some don't. Some are 1 AP per every other classroom. So if let's say they have an 11N solution, but they really have outgrown their 11N solution, or even an 11AC solution, and they've outgrown it, and they want to think about going to the next, they don't want to pull, additional cable into their classrooms that currently don't have APs. Well, let's go to use case number 2 with multi-user MIMO. Everything is the same except now we have Wave 2 clients. And again, Wave 2 clients are here. I'm sure not everyone has a Wave 2 client in their pocket currently, or their tablet's not Wave 2. But fast forward in a year from now, and a lot of folks will be carrying Wave 2 clients, knowing how quickly we refresh our tablets and our phones. All right, DFS channels available, same. Everything's constant there. And let's see. Now with Wave 2, we do the same math. But what's different here is I don't have tables for Wave 2 yet. I'm working on those. I will create some tables based on some more testing that I have to do. But using that 50%, we'll just say that now we have a channel capacity of 208. So with 208, if we have capacity, we do the math. Now it's 1.9 of airtime per device. And then multiply that, and we come up to 48%. So, in this particular use case, if we had a Wave 2 solution, not just the C120, the C120 could have been used for the first example without multi-user MIMO because we had Wave 1 clients. So that would have been fine. And future-proofing for the time when you do have Wave 2 clients. And then you have Wave 2 clients in the second use case example. And now we can basically get by with doing 1 AP for every other classroom, or 1 AP for 2 classrooms. And I didn't factor in 2.4 because if you look at the ratio between what's available in 2.4 assuming there's no interference in 2.4, just you have one 611, which is in a lot of places that's not true. You obviously do have a lot of interference in 2.4 from neighboring APs or from interfering devices and microwave ovens and so on. The ratio right now is like 8-to-1 in terms of spectrum. 8-to-1, 5 gigahertz to 2.4. In the future, it's going to jump up to 12-to-1. So the reason why I don't factor in 2.4 is because it's such a small fraction of capacity compared to 5 gig. So I recommend doing the design around 5 gig. And, 2.4 is there. You're going to get something out of 2.4, but let's not factor it in. Let's, consider it as kind of a little bit of a buffer, if you will. How much, it really depends. All right. So takeaways. Wireless LAN should be designed for capacity, and what we just did there was a capacity design, a simple one. And classroom use cases can require high capacity. On aggregate, you have 25. We use 25 devices there, but it could be up to 40 devices. And what if they want to do a 5 meg SLA? Then you're probably going to need 1 AP per classroom to do that. Of course, you have to use 80 megahertz channels in a lot of cases. We recommend using them, especially if you don't have a problem with DFS. And even if you do have DFS, you can exclude that DFS channel, or maybe a couple of DFS 20 megahertz channels, from the the pool or candidate list of channels. Right? Most systems let you do that. Certainly, Mojo Networks allows you to do that. So you can still use DFS. You just maybe can't use 1 or 2 channels because you're having radar events on those particular channels in that particular area. So I think we're past the point where we have to stop, being paranoid about using DFS channels, because that's where all the spectrum in the future is most likely going to be DFS. So we have to get used to that. All right, 11 AC Wave 2 APs are here, obviously, like the C120, and the also 11 Wave 2 clients are here. There's a lot more than what I showed you. There's probably I showed you probably about 1/4 of the ones that I'm aware of. So again, there are a lot more. Let's see, Mojo Networks. Yeah, we say it's a true Wave 2 because of the fact that that's 4x4 spatial 4x4 spatial stream multis and MIMO. So we can have to have up to 4 clients simultaneously, or use 4 spatial streams simultaneously. And it's a 160 megahertz support. And so, knowing that, it's a way to future-proof your network with the 160. Wave 2 solutions can scale higher. Yeah, obviously, with besides the fact that the 160 megahertz support really is what lets you double right away. Again, you can't use that in most use cases, but future. But also multis and MIMO. Right now, we're saying 50% boost in performance, but who knows? You could conceive, if you think about it, if you have a conversation with all 1x1 clients, and you're doing that serially with Wave 1 versus 1x1 clients where you're doing it up to talking to 4 at a time, you could see it, once we all get better at it, and that's on the client side and the driver side, the chip manufacturer and so on, you could see where you can get 100% boost in performance for that particular, use case. But we haven't seen that yet, but we're expecting to approach that. So opting for a Wave 2 solution can lower your TCO. If you can get more out of a single access point, and we're sure you can if you're using a Wave 2 solution, then you can end up meeting the requirements for fewer number of APs. All right, so those are the main takeaways. Then I'm going to go on to Q&A and take a look here. All right, so yes, let's see. Will Wave 2 APs improve performance of Wave 1 clients? So that's a good question. And if they do improve performance, and I think they will, it's not because we're getting any Wave 2 feature functionality out of the Wave 1 clients, because the Wave 1 clients are not going to support multis and MIMO. But here's one way that they could improve performance. Not all Wave 1 APs supported beamforming. We didn't talk about beamforming too much here, but that's just TX beamforming. We're not talking about multis and MIMO, although it is part of multis and MIMO. We're just talking about using beamforms to improve this SNR, signal strength, for a single client. So still using SU-MIMO, single user MIMO. So Wave 2 APs have to support beamforming because if they don't, they can't do multi-user MIMO. So in that way, they could help the performance of with Wave 1 clients. Also, as APs get better, they have more CPU, typically more RAM, better, just better radios, receivers, antennas. I mean, we've all gotten better at this. So every generation of AP, we see an improvement there. And all of that can help improve performance with 11N clients or 11AC clients, even legacy clients. So there's that as you go to the next generation, like Wave 2. Next question is, do you recommend 160 megahertz? Well, today, with the only and very, let's say you had a completely isolated deployment where you had high throughput requirements. You didn't have high density requirements. High throughput is not the same as high density. So we're talking, maybe it's 20 clients, but each client wants a, 20 meg SLA, and they're Wave 2 clients, of course, and you wanted to be able to support a 20 meg SLA. Well, if that was an isolated area where you didn't have to worry about channel reuse or overlapping channels, there's nothing stopping you from deploying 160 megahertz on that one AP in that area. And so you could do that for high throughput, not high density. For high density, you'd want more radios, so you'd end up using smaller channels to accommodate the very high density. But yeah, 160 today, not likely in education, but in the future, as we have more spectrum, likely, at least in certain areas. When will the C120 start shipping? I don't know about that. I'm gonna have to get back to. By the way, we'll follow up with these questions. We'll have the answers in writing, and we'll send those out to everyone. So I'm gonna have to get back on the 120 shipping. Does the C120 support beamforming? Yes, it has to, because again, to support multi-user MIMO, beamforming is a critical part. Remember, we're using beams and null beams. We're trying to create constructive interference at the receiver or destructive interference for the non-receiver of that information, so to speak. Okay. Do you recommend running 2 Ethernet cables to a C120? Yeah, good question. Somebody may have done the math, and let me see if I can go back to this slide here. I'm going to jump back to okay. All right. So if we have 800 megabits per second max data rate, right? Not throughput, but max data rate on the 2.4 gig radio, and we have a 1.7 gigabits max for the 5 gig radio. If you do the math, now just take these two, add them up, and then just do half. Well, or say so you're not getting or say 1.3 plus 8, so you have like 2.1 gig, 2.1 gig of a max data rate. So if you had a MacBook Pro connected to the 5 gig radio, a MacBook Pro is going to connect at 1.3 gigabits per second max. And then you had, let's say on the other side, you had another MacBook Pro, and it was connected at 450 megabits per second. We'll say that it's just a 3 megabits 11N on that side. 3 spatial stream 11N on that 2.4 side. So right away, that's that could give us 1.7-ish gig of a data rate. So if you go 60% of that, and you're already over, you're basically going to oversubscribe a single Ethernet gigabit per second uplink. So there are 2 gigabit ports and does support link aggregation. So that way you could have 2 ports connected to an access point. So you could get over 1 gig of aggregate throughput. Should you do that for all of your 120s? No. If it's a greenfield deployment and you want to run 2 cables to, where you might have high throughput requirements, it's a lot cheaper to run 2 cables at a time when it's greenfield than to go back in and, run another cable. So it's something to consider for very high throughput environments. Because the AP is capable of oversubscribing a single gig Ethernet uplink. So something to consider, but only in greenfield really, and where you're going to have high throughput environments. All right. Let's see. We have some more questions. Let's see. I guess, do we have any more questions? Erica, do you know if I guess that might be it?
Yeah, I don't see any more coming through. Thank you for all those who submitted questions, and Robert for taking the time to answer these. Of course, if any questions come up at another time, you can feel free to contact us any of these through any of these channels below that you'll see on the screen. You can contact Robert directly, either through his email, rf@mojonetworks.com, or his Twitter handle. Additionally, you can feel free to visit us on our website, mojonetworks.com, visit us on Twitter or our blog, and feel free to reach out to us through any of these channels. We will get back to you. Final piece that we'll be addressing is your free access points. So all those qualified attendees who are on the call today, we will be reaching out to you to confirm and qualify your access point shipping details. So as just a side note too, all of our valued partners and resellers and any partner engaged in a current promotion is not eligible for a free access point. But again, you will be contacted by your Mojo Networks representative to confirm your shipping details. If you have any questions, feel free to call us at the number below or send an email to myrep@mojonetworks.com, and that will go directly to your representative who will contact you about your free access point. And that is all we have today. Please visit our website. We have new webinars that we are adding, and we have a new schedule that has just been posted. So quite a few coming up through the next month, and we even have an additional webinar coming up with Qualcomm to talk more about Wave 2 technology and our C120 model. So that would be a really great webinar if you are interested in learning more about Wave 2 in general. All right, thank you very much for your time, and have a wonderful day.
Thanks all.